Good afternoon, everyone. This is Janice Oliva. I'm the president of ISE Magazine. Welcome to today's ISE webinar, FTTx OSP Considerations, presented in partnership with Light Brigade. Before we get started, though, please remember if you've requested to receive a BICSI continuing education credit, you will receive 1 credit for attending this live webinar. But please note that the BICSI CECs are not available when you view a recorded one, just for the live ones. And also, please share that with your teammates for the future. So now we'll start to talk about the FTTx OSP design considerations webinar today, which is going to be focusing on cost-effective planning of FTTx network designs, fiber feeder routes, and proper splitter placement for PON or active Ethernet systems. This introductory session compares and contrasts distributed, centralized, home run, and point-to-point network field configurations to the outside plant. The content examines design benchmarks and installation parameters for high-rise buildings, campus-style apartments, single-family residential areas, and rural areas, as well as the impact of dynamic issues such as take rate and density on economical deployment. As attendees, you will gain an understanding of how to logically make OSP design decisions based on a variety of inputs, including client type, densities, distances, and installation challenges. They will also learn how the type and locations of optical splitters and associated hardware, including fiber distribution hubs, fiber access terminals, and termination methods, which all must be considered in the OSP design for FTTx installations. You will also understand how current and future densities are major considerations when designing FTTx systems. Our speaker will start with an introduction to FTTx OSP design and then share the fundamental fiber plan for you, followed by urban and rural design options, and we'll wrap up with a very helpful Q&A which you will be providing for us, and our speaker will be responding. But prior to that, if you haven't already, I know I say this every time, but please do subscribe to our publication, ISE Magazine. It is the how-to resource for you ICT providers across the globe. The link is on your screen as well as the information tab of this webinar. So now we're going to go into today's webinar. Oh, we got our magazine going across there. There we go. Today's webinar would not be possible, of course, without our sponsor, Light Brigade. Since 1987, Light Brigade has instructed more than 50,000 attendees in its public and custom classes. The company offers nationwide courses that cover basic fiber optic design, maintenance, and testing, as well as industry-specific topics such as FTTx, where the company has developed industry certifications and provides both open and customized training courses internationally. The company offers course development services and will custom create a course to any fiber optic subject matter or skill level. In addition, Light Brigade produces professional quality educational DVDs and online training. All of Light Brigade's training materials are technology-based and demonstrate theory and techniques applicable to any manufacturer's products. Please make sure you visit www.lightbrigade.com. Now, I hope my slide is going to progress properly. So now you should be seeing our speaker. Let me introduce you to him. It's John Drawn. He is a graduate from Montana State University from 1986 with a Bachelor's of Science in Business Marketing. He soon gained work as a fiber optic technician with a small fiber optic service firm. And for over 17 years, John has worked as a technician, consultant, instructor, project manager, and business owner in locations as widely varied as Thule Air Force Base in Greenland and the tunnels beneath our great city of Chicago. John has been an instructor with Light Brigade since 2015. So thank you, John, for joining us. Before we get started and let John take over, there's just a few logistics about the webinar. You'll see here on this page the information tabs at the top of your screen will allow you to find out more information about our speakers and sponsors. The Event Resource tab on the left side will allow you to download a copy of the slides from today's presentation at any time during this webinar. And finally, you can submit, and we ask that you do send us many questions throughout the presentation using the Ask a Question tab. And we will hold these questions until the end of the session, which at that time we'll answer as many as possible. And if we don't have time to answer all of your questions, we'll take your contact information and reach out to you afterwards offline. So with that, I'd like to hand our webinar over to our speaker, John. Go ahead, John, take it away.
Thank you, audience. Welcome to Light Brigade's FTTx OSP fiber design. FTTx is a large group of applications. The industry didn't really want to pigeonhole it to fiber to the home. There's a lot more than just FTTH. There's fiber to the multi-dwelling unit, fiber to the desk. There are companies and actually municipalities that are bringing fiber to the camera, fiber to the traffic control system. The fundamentals that we'll talk about today will apply regardless of how you're getting the light to the end user. Bear with me just a moment while I start the next slide. The Light Brigade has already been introduced by Janice. I won't rehash that, but we do offer some classes that might be appropriate. The Certified Fiber to the Home Professional, there's an outside plant design class, and we also have one with a lot more hands-on for installers and technicians. So if you define the two standard types of design options, one on the left side has active electronics that are dedicated to each individual customer. The capital costs for those electronics are substantial, which makes the right side in many cases more attractive. We call that passive optical network, where a component actually shares the light among multiple users. One of the advantages of an active system is that because you have a dedicated transmitter to each individual user, the bandwidth can be symmetrical. In other words, high bit rates downstream as well as upstream. Throughout this program, we will talk about what's the most economical place to place your components, the layout of your feeder cable, the directions that those should be laid out, as well as an economical cabinet size. But first, I'd like to review the various design types. And this is an active system with a cabinet. The things that need to be considered when deciding on this type of topology is that power will need to be provided to that cabinet, wherever it's at. And active systems transmit from whatever location you decide. So the topography of where that cabinet is located, whether it's mounted on a pole or placed on a concrete pad, power, as well as backup power, batteries, have to be considered in the cost study that should be done and whether this system is appropriate for your users. One of the advantages of this particular type of design is it's not drawn on this particular slide, but if you were to draw another line back to that large building on the left from the cabinet, that would provide redundant routing. If we had a separate fiber cable feeding that cabinet, And this becomes important when certain users require a higher level of service. We call this topology home run. Individual fibers are assigned to individual customers. So they start in the central office. We could also call that a node or head end, depends upon your nomenclature. But it's a fiber-rich topology. It's also identical to a home run in a passive system, where if we put the splitters in that central office. Things to be considered when deciding whether a home run is appropriate: the cost of and space requirement, the terminations for all the fibers, jumpers that are going to carry over from your transmitter to each individual patch panel, as well as the space, rack space, square footage on the floor space, all the power requirements. And again, there is no difference between the outside plant design in a home run passive optical network and an active Ethernet design. It just is, it's identical in the outside plant. In a passive design, the splitter is the heart of the network. It does not require electricity. It's a passive component, hence the name. They come in a variety of configurations. Then there's a multitude of options in terms of configuration, whether you have them connectorized to place inside of a cabinet, or bare fiber to splice into your outside plant in a closure. There's a couple different design types. There's planar. FBT stands for fused biconic taper, which is a method that they're manufactured. Typically those are smaller counts, but they're very small in profile. So in some cases they would only occupy one slot, similar to the space required in a heat shrink sleeve for a fusion splice on optic fiber cable. One in, multiple out. So you're sharing the power from your transmitter. Economically, this has a huge advantage because you amortize the cost of that electronics over multiple users. They are sharing bandwidth. On the disadvantage side, you're taking a substantial decibel loss. These introduce, they are sharing the light, they are splitting the light, dividing it between users, one in, multiple out. So depending upon how many times that is divided will determine the total amount of attenuation. So the payout, the disadvantage is that your distances are reduced in passive systems as compared to active, which since you have a dedicated transmitter, it can go without any componentry in between start to finish. Typically, every time you divide the light, you lose about 3 dBs of attenuation. In the design process, we suggest that in the beginning, an area be divided into PON units. Typically, the standard calls out a 32 split. If you follow that standard, then you would divide your area into 32 groups of users, whether those are homes, apartment dwellings. And this is important not only in the beginning stages to be able to locate the appropriate places to place your components, but records management. So once this network is completed, the assignments of those splitters to individual units becomes important in terms of records management. 32 is not the only one. There are options to reduce that to 16 or even go up to 64. The trade-offs are going to be sharing the bandwidth. You're dividing that signal even further. the names that we give, the three different passive options, home run, centralized, or decentralized, are determined by the place that we, the location, the physical location that we put the splitter. If we locate all of the splitters in our central office or node, we call that design home run. It is identical in the outside plant when you compare it to active home run, because each individual user has a fiber that travels from the central office to the home or the desk. The economic advantage is it allows you, when you place your splitters in a location like this, you can grow incrementally, spend only capital cost on a transmitter and splitter as your customer base grows. That same argument would hold true for a centralized. Centralized, we move the splitters out of the central office and put them in a cabinet. We could call that a splitter cabinet or a fiber distribution hub. This cabinet does not require electricity. All the componentry within it are passive, which is one of its biggest advantage. The cost of the right-of-way, the concrete pad, the mounting of that location, those all will add capital cost to your build. But in terms of passive system, you gain the advantage of sharing the power, sharing the bandwidth among multiple users. Now, how many, the splitter count, if you follow the standard, be a 32 count splitter. Later on in this presentation, we'll talk about what's the best appropriate size, how many splitters should we put in a cabinet, what's the most economical size. But at this point, I just wanted to talk about the concept of centralized splitter. Again, the economics of having a cabinet allows you to add splitters and optical line ports or optical line terminals. The electronics that feed that splitter can be grown incrementally. So in other words, if you have 30 customers that sign up day one line port and one splitter will suffice. When customer 33 signs up, a return visit adds a splitter and the line card, optical line terminal, until you gain another 32 customers. Depending upon your growth rate and your take rate, that may be an advantage. One of the advantages of having a cabinet, incremental capital cost. Another advantage is if troubleshooting access. You have a segmented link from the central office to the cabinet and then the cabinet to the home, which may provide an advantage or access for troubleshooting. On the disadvantage side, connectors are a weak link. Anytime you put a non-permanent connection into a system, they are it is a weak link in the network. And there's a large expense involved with the acquisition of right-of-way and all of the requirements and actually placing them in this location. Another name for that cabinet could be fiber aggregation point. So in this next slide, we've removed the cabinet. Now we need to decide where we're going to place those splitters. We're essentially pushing them away from a centralized location and closer to the individual users. Where we physically locate those, we could put them in a splice closure. We could put them in what's called a fiber access terminal, which is basically a pedestal that is mounted on the ground. We could. There are several different options in terms of where those splitters could be placed. And you don't necessarily need to maintain a 1x32, a single individual 1x32 splitter. You can have combinations of splitters, a 1 into 4, which then feeds 8, feeds 4 1 by 8, which mathematically is of the equivalent of 32 splits. One of the disadvantages of this design type is that all the capital cost for line terminals and splitters has to be in place day one, because you don't know who's going to sign up for your service, and you can't incrementally add those items as you grow. So that is on the disadvantage side. On the advantage side is that it substantially lowers your distribution cable counts, because the fiber required to feed homes is reduced, and we'll illustrate that in a couple slides here. And another advantage is that you've now eliminated the cost of right-of-way and acquisition for placing a cabinet, as well as the cabinet itself. So just to be redundant, the centralized and home run configuration initially use the least OLT ports, and that's what I was saying, that when you roll your system out, if you only have 30 customers, 1 transmitter and 1 splitter is sufficient, and with the cabinet and the home run, you have the flexibility to incrementally add those items as your network grows. Excuse me just a second, we had a little gremlin in the works. So this slide illustrates some of the split options. So if you were going to go into a neighborhood and do 1 by 32, so each pawn area basically gets 1 splitter, and if you're using a number of drop closures, let's say 8, 4, that 1 by 32 might feed 4 drop closures. That's an option, but the 24 fiber will feed. When you look at the next line down, we have a 1 by 4 splitter feeding 4 1 by 8. So the total split count in the end is the same, but the fiber count required to distribute those fiber, that light, providing pathways of light to all the individual users is reduced. And you could reverse that and go 1 fiber from your central office into a 1 by 8 splitter and send that light to 8 1 by 4s. The split count in the end is still 32, but you've done it a little bit differently. And then very bottom line is what's called an unbalanced splitter, an uneven splitter, where in a linear relationship, each splitter is selected for its pass-through as well as drop power. So, and these can be attained in a variety of configurations. For example, 100% of the light comes in, 90% continues on, and 10% is dropped to your customer because it's very close to the transmitter. That has some inherent disadvantages, because when you can start adding customers that are downstream, you have to design it so that you actually have to know what the incoming power requirement is, as well as if you have to cut the fiber to drop that customer or to splice them into the network. This is our first color slide, and it's one of our. Graphically, it represents quite well one of the advantages of a distributed split. In this case, we're using a 1 by 32 splitter. We're feeding an area of 256 homes, so we're going to require about 8 splitters to make that happen. And where we locate those splitters, it could be in a variety of configurations. Could be in a splice closure, an access terminal. But the green outline defines our PON area. Our central office is located on the right side. So the pathway of light is going from left to right. Blue fiber feeds that first PON. We backfeed 16 fibers towards the central office into drop closures. And then 16 fibers go downstream and feed 2 more drop closures. The most important thing to take away from this slide is that as we move from right to left going downstream, in the next PON area, the fibers that we used for distribution in the first one become available for use in the second one. The only dedicated fiber is orange out of blue tube, which is feeding that second PON. So we can't disturb in the second PON fiber 2 through 8, but blue is available as well as the ones that we used in the previous PON. And so fibers are reused from PON to PON, and so the ability to serve a substantial number of customers with a very modest fiber count makes this an advantageous design. This next slide, we moved from a 1x32 split, a single individual 1x32 splitter, a component of that size. We've decided to go one fiber into a 4 split, which feeds a 1x8 split. So in the end, we still are dividing the light 32 times. So the attenuation values is it's close to the 32 count, but you add each individual component adds a little bit more. The theoretical loss for a 1x32 is 15 dBs, but when you start manufacturing tolerances and that type of thing, you're typically looking more like 16 dBs. And so these individual components add a little bit more, but it provides some flexibility. So if we look at the pathway of light, where our central office is still on the right side, we feed blue fiber into that 1x4. We backfeed since orange isn't being used there. We can backfeed to that 1x8 and then go forward into 3 more 1x8s. Now, keep in mind that these splitters, since they're small count, they could be fused by conic taper type, and they're small enough that those could fit quite easily into a single slot in an organizer tray inside of a splice closure. But the number of customers that you can feed is quite substantial. On the disadvantage side, this requires a lot of really good record keeping. Where are your splitters, and who are they actually providing the light to? So the choice of which design that a network designer would choose the customer take rate, the density of your area, and the labor rate all come into play. If you decide to go connectorized drop cables, labor rate becomes really important. Is it worth saving money on the installation side, having everything plug and play, or do you want to build it as you go and actually splice? Costs are related. Selecting one design type will affect all the other elements in your network, which have a relationship in cost. If you go with a home run, your feeder cable is going to be high count. If you do a centralized cabinet design, your feeder cables counts are going to be reduced, which changes the cost relationship, but now you have the cabinet itself as well as space and location. You're going to go with the connectorized drops, you're going to splice those on. all costs are related, distance and density. One of the big questions that what needs to be answered is where do we place our elements in our network, our hub, head end, central office, node. Physically, where should we place that in our area? From that location, how many feeder routes are appropriate? Where should they be placed? Where should our branch cables go? How do we define the boundaries that those cables support? Which customers are those cables going to support? And then finally, where are we going to place splitters? So if you take an ideal world and apply it to the real world, it assists in making that determination. So this idealized planning model has been around for many years. Take a perfect world. Each street is even, 500 feet long, 500 feet wide. Our density is consistent, 32 homes in each little box. We call it a pond. So in this area, we have 2,048 units. It's going to take 64 1x32 splitters to support it. And using cost studies, we place the node in a variety of configuration and then add up all of the pieces and parts that it would be required to support each unit, each individual pawn. And I won't keep you in suspense. The best design is going to be in the middle. So diagram 1, where we've placed our central office in the center, answers two fundamental questions, which I brought up. One, where should we place the central office? And two, how many feeder routes and how should they be laid out? Are answered within this one cost analysis. Figure 1 has the least amount of elements to serve all of the customers. By placing geographically in the center, it minimizes the distances to all users. But now I hear a question in my head. Why? It's not a perfect world. Nobody's got even density everywhere. What about that effect? Well, yes. By looking at an area and analyzing changes in density, it is true that an adjustment should be made, but it does not take much to economically satisfy the equation. In other words, don't be putting it in the center of that dense area. Just make a minor adjustment. And you can run your own cost studies of how far is appropriate for your network. This is an ideal planning model. And if you have an idea going in what the ideal is, the closer that you can approximate to that, the better off your costs are going to be. This next slide is a good graphic on supporting the argument that placing an element that serves an area is better off in the middle. So we have a total of 288 homes. And this could be the node, it could be our cabinet. We're doing a home run, bringing all the fibers to that one location. With 288 homes, we're going to need a 288 fiber cable to support it. We don't show the bores that go underneath the road, but to get from the node to all the homes, that high fiber count cable is going to be a requirement. If we put it at the very end, if we put it in the middle, bear with me here, my slides. If we put it in the middle, we cut our fiber count in half. Makes common sense. If you now the total distance of fiber is still the same, but the fiber count is reduced. So any outside plant device that serves a geographical area should be placed in the middle of the area it serves or as close as possible, whether it's a central office, a node, splitter cabinet or active cabinet, individual splitters, right down to the drop closures. If you put those in the middle of an area, that's going to minimize the distance to all the users. It's going to be the most economical. If you have a density, adjust for it. The closer that you can make it to the ideal, your better overall cost structure is going to be. Which brings us to the next question that I have is how many feeder routes? I've already given you the answer. We looked at it in diagram 1. How many and which way they should go, and then what direction our branch feeders should be, and then the boundaries that those feed. Drop down to the last bullet point. Design your outside plant with 4 main feeder routes: north, south, east, and west. Branch feeders come off at 90 degrees from that main, and then we assign the boundaries, the serving areas for those cables at a 45 degree from our center. It's going to be the most economical outside plant layout. It minimizes the distance to all the customers. And regardless of whether you're running copper or fiber, it's the most economical choice. Now, in the middle there we say, okay, we're realists. It's not an ideal world. But if you can attempt to make it as close to the ideal as possible, that's going to be the least expensive. We call it the pine tree. 4 routes come out of the central office, north, south, east, and west. Our branch cables come off at 90 degrees to those, and then the dotted lines are our serving boundaries. So this is part of the fundamental plan. We look at an overall area, and this will also give us some fiber count and sizing. And in this fundamental planning process, we would be identifying different types of users. Residential areas are going to be different from high demand users. Imaging centers, hospitals, call centers, data processing centers. If you have an area that needs to be fed with an active system because they demand higher bandwidth, asymmetrical, high upstream, high downstream, and a higher level of reliability, there's nothing that says you can't blend active and passive into a design topology. And you can create mini rings, little mini rings. We say overlay active on top of passive by connecting the outer branches. Upsize your cables to meet the needs, to make those happen. Plan for both. Activate them as you need them. So we've got our pine tree. We've overlaid it onto our area that we're going to serve. And then we identify those particular users that require an active system and route redundancy, and we tie the branch feeders together and create ring architecture. Both technologies have the capability to deliver. Use them where they make sense. Passive optical network for small business, single-family homes, and then active Ethernet for the high-end users that require dedicated bandwidth and a higher level of reliability. blend them into your fundamental plan. So this is an example of a small town. The little blue dots represent users. We definitely have a density effect here that we would adjust for. We overlay our ideal model, determine where our main feeder routes in blue are overlaid on our area. The green lines are railroads. We have to keep that in mind in the physical world because those present their own set of challenges. The red line is how we are going to determine the boundaries that our main cables feed. And then we end up with a topology that we massage to fit the real world. Now, you do the best that you can given the challenges that you face. Railroads present their own set of challenges. User density and bandwidth requirements will change your profile. So in this case, we didn't go due north because there wasn't anybody to use the glass up there. And there was a determination by the customer they would rather connect to another city. There was no need, so it comes out of the city and turns to the right and goes north. To future-proof your network in the fundamental planning process, look at all the potential users. If your city has safety cameras as part of the municipality, are they on fiber? That presents a whole new class of users. Traffic lighting. Security. Use good judgment. Plan the route. Lay out all of your cables, their cabinet locations, who's going to be served and by what, where they fall within the boundary. Have a multi-year plan. Be consistent. Make modifications. Keep good records. And that final statement is, don't design the network with the thought process of going back in and rearranging fiber counts to meet the need. Be proactive. Plan on having the appropriate fiber counts to feed the future and not have to borrow or reroute because no matter how good your technicians are, it's never, whenever they have to go into a live system, there are risks involved. So the other question I told you we would discuss is how big the cabinet should be. We talked about where it should be geographically. We're going to place it in the middle of our serving area. But what size? What's the appropriate size? How many homes are going to be served by that cabinet? Well, we go back to our ideal planning model, and by putting the cabinet in the center or in a number of different locations. So let's look at the two extremes. Two cabinets serve our 2048 area. Look how much blue there is. That blue is your distribution cable. So a scenario like this is going to have a substantial amount of distribution cable. And then the other extreme is each 32 area gets its own cabinet. So that, on the cost equation, is going to be cabinet heavy. So you save on your distribution cable costs, but are heavy on the cabinet costs. So the question is, where is the happy medium? Well, through a series of cost analysis by using a variety of cabinet sizes, comparing all of those costs, 256 to 288 is the most economical. It balances the cost of the cabinet compared to the cost of your distribution cables. that brings us to the end of our webinar. Janice, are you there?
I was on mute. I'm so sorry. I didn't want to add any distractions. Thank you so much. This is great. We do have several questions that I want to cover, so I appreciate everyone sending those over. And thanks so much for your patience with a couple of things with audio as well. Learning about Chrome, not wanting to play nice with this platform. So thanks for being patient. So we're going to move on here. Why isn't the home run design considered an active design? Why would you place a splitter in the CO? That's our first question, John.
Excellent. The design itself reflects the outside plant design. In other words, the fiber cable that feeds the central office. So regardless of whether you put active electronics or splitters, the outside plant is the same. And if you look at cost analysis, there is actually a relationship. If you look at the cost of a cabinet, if you're thinking about cabinet costs, within the first 4,000 feet, it's actually more economical to run fiber to the central office from each individual home, as compared to building a cabinet to serve that area. So around 4,000 feet, so that the cost of the cabinet outweighs the cost of your cabling.
Okay. I hope that answers that. You want to say anything else on that subject, or are we good?
That's all I have to say.
Okay. Great. So we have another question here. What is the advantage of centralized pond design?
The biggest advantage is economical. So when you do a centralized and place your splitters in a centralized location, you can incrementally grow as your user count, your user base grows. So if you have a take rate that supports a slow incremental growth, a cabinet is an appropriate choice because of the fact that you can pay with future dollars the splitter and the transmitter required to support groups of users. So let's say you roll out the system, and for number's sake, let's just say this particular area only has 30 homes that sign up out of the cabinet. It's going to eventually support 256, but from the first week, only 30 homes sign up. Well, you only have to pay for one splitter and one optical line terminal port to begin with. Then on customer 33, actually go back in and add an additional splitter as well as line terminal port to feed that next group of 32 users. So depending upon how long it takes for you to add homes or end users to your subscriber base, it may economically be more advantageous to do that. Both the home run passive as well as centralized allow you to add splitters and line terminals as you grow.
Great. That is always good. Cost effectiveness. Okay, another question here. What are your thoughts about tapering fiber cables?
Oh, excellent. We really didn't cover that much in this slideshow, but so tapering, look at the cost of splicing a location compared with continuing that same fiber count to the next drop point or the next splice point. So if you have a 72 fiber count cable and you're going to drop to 48 count, for example, one could place a 72 and then use a separate cable and run the 48. So you'd have 48 splices in that one location. Look at the fiber splicing costs and compare that with running. If you don't need to access those fibers at that drop location, it may be more economical to run that 72, continue it farther, because the cable count, look at your cable count, the individual per foot cost, and compare that to what it cost to splice a location. So if you don't need to actually, if it's not the end of the reel per se, and you're just dropping count size because you don't need those fibers, it may be more economical to continue that higher count for another few hundred feet. Depends upon the cost of your splicing, and you compare that to how much cable it's going to take.
Okay, very good. We're going to move on, and can you double up and use existing traffic controller cabinets as a question?
Yeah, well, it depends upon where you're going to put in them. If you have the space, if you're going to do a distributed split, the splitter cabinets are designed to, they have patching functions and splitter mounting, and there's parking areas, and then cable management internal to them. So an existing cabinet not going to have those functions built into it. So depending upon what your end goal is to achieve, if you have the room to place the management hardware required to manage cable slack and jumper count, and depending upon what you're trying to achieve, if you want to have a patching function within that cabinet, there's nothing necessarily wrong with using the existing facility, as long as it's got the room and to mount the hardware required to make it secure and organized, and then be able to grow in a high quality manner.
Okay, yeah, that makes sense. You don't want to sacrifice quality for sure, especially if you're starting with such a quality product. Okay, we've got another one here. Is a cabinet really required for a pond split? Question mark. Could a 1:32 splitter be put in a vault or a pedestal?
Absolutely. In fact, there are vendors that have a split patch function within a splice closure. So no, a cabinet is not a mandatory requirement. It has advantages and disadvantages, just like many things. If you want to place physically where you place that splitter, there's a few different options. It could be in a vault. It's got to be protected. In other words, it needs an environmental capsule, but that is a splice closure. So that it's quite easy to do. There's a lot of options in terms of vendor hardware that's available to make that happen.
Okay, sounds good. Another one here is a quick just meaning question. It says, what is the meaning of sealed outside plant?
Sealed. Great. So you plan it, engineer it, construct it, and then if you've done all of your homework, hopefully there isn't a lot of return visits to make rearrangements. So in other words, if you didn't plan ahead and you didn't choose the appropriate fiber count size, it's never a good idea to borrow it from other parts of the network when it wasn't originally designed for that. So having repeated entries into closures and reconfiguring fibers, pulling them out of splice trays and rearranging and and that type of thing, we recommend against it, and that's why we say seal it. Plan it, engineer it, build it, and then leave it alone.
Got it. I like it. Secure it really well so nobody else can get in there and do that too. Okay, so John, we have a question. He says, John, what's the source of the cost analysis you keep referring to?
The source?
In other words, where are you, yeah.
S-O-U-R-C-E.
U-R-C-E, like where are you getting that cost analysis data from?
So the author of our fiber to the FTTx OSP design, David Stallworth, wrote and spent many years as a Bell engineer, consultant, design analysis, freelance author, and he is the cost study master, and he has created a variety of spreadsheets where one can experiment with a variety of configurations, changing the pieces and parts and seeing what the net effect is, and that's where those results are from.
Okay. Where might Jason get a hold of that, in case he wants to know that type of...
Probably put him in touch with David, if you'd like to do that.
Okay. So you can connect with John, Jason, if you'd like to, or anyone else, and we could do that. Okay. Small village cable starting from scratch, covering 200 subs. Is it more economical and easier to install than coax and amplifiers? Sounds like a word question.
Yeah. I know very little about coaxial and the requirements for designing a system, so I would have to defer to an actual coax engineer to answer that, so I'm unable to truly move that forward. I may be able to put that individual in contact with somebody that could answer that more appropriately. Okay, sounds good. Not my area. No problem. You can't be an expert in everything. We realize that. Let's see. We're going to keep going. We've got several more actually here. When running design models for cost-effective deployment, where do you get your cost data? I think that might relate to the source question. That was that same. Okay. Yeah, there's a variety of cost equations. All right. Next one is, in the case of centralized network, how do you manage new installation costs, and what is the marginal cost to install a new user? The marginal cost to install a new user is going to be network dependent, whether they're aerial or underground, the type of drop cables, whether they're connectorized on each end. So that cost would be part of your fundamental plan, whether you go with a pre-connectorized drop arrangement where you build everything and then running your drop cables is just a matter of plug and play, or if you actually require your installation team to terminate the fiber at the customer's home, run the drop over to your network, and access either a terminal, a fiber access terminal and a pedestal, or if you're doing splicing in a closure, there's a variety of hardware and design type topologies. But how much that would cost would be dependent upon the choice that you made to begin with. Right. Your design, your starting point. Okay. The record-keeping demand of distributed split seems really high. Are there ways to add that into a comparison with centralized cabinet, centralized/cabinet? Well, there's just a couple elements that need to be added. And so your accuracy, that each individual item that you need to keep a record of adds overhead. So if you have all of your splitters in one location, keeping track of that one location is going to be less than if you have your splitters in 5 or 6 or 10. So that's the difference, and depends upon the sophistication of your engineering department, and it's just a matter of the feedback of data. If your company is really good at keeping records and then the process is intact, it's not that much of a burden. But if you're weak in that area, then that may not be appropriate and may not be appropriate choice for you.
Mm-hmm. Yes, definitely. All right, we've got 3 more questions. I'm going to keep running it. I realize we're at the 2 o'clock hour, so if some of you have to sign off, we will get back to people as well of questions that are not covered here, but I'm going to keep going. We have 3 more. So what application would you recommend to properly record end user details in a distributed split environment?
The application in terms of software, there's a variety of softwares out there that provide network management. Internal spreadsheets. Depends upon what infrastructure is in place. Don't necessarily recommend any particular make or model at this point, but whatever is appropriate for your company.
Right. I know it's hard. There are quite a few out there. Okay, so we've got here, why is the cost analysis of a cellular duct using microcore fiber in OSP design for air-blown fiber versus traditional smooth wall duct? Or excuse me, what is a cost analysis, not why. What is a cost analysis versus microcore fiber OSP design for air-blown fiber versus traditional smooth wall duct? Again, I think it depends.
That would be, you just run your own cost studies, look at the cost of hardware and installation labor between one to the other. You could actually submit, if you're looking at if you have some engineering done, you could submit a request for quote for either one and then do your own cost analysis. It's going to depend upon where you're at. The availability of air-blown fiber is a little bit more specialized than just pulling cable. So that's going to add a different element. If you have contractors that are available to do that and are competitive, that'll change your profile.
Right. Okay. Let's see here. I think there's one more, and that would be, what application would you recommend? Oh, no, we did that one. I'm sorry. Someone asked a question, which is cost-effective coax or fiber in a 200 subsystems. He says, I'm a coax engineer. Feel free to forward my email. Okay, thanks a lot. All right, last question. I love it. Can you recommend a geospatial solution that can be used for FTTx records management? There's several of those out there, too.
Yeah, I would. There's a variety of vendors, and I would contact them and see which one is most appropriate for your cost structure. How much some of them are charged by the hum passed. It depends upon the vendor. Right.
I know, if you go into the ISE Buyer's Guide, we have a lot of them listed there and easy access information. Within that, you can go into our website and check that out under categories. So that would be fine. And with that, I think we've covered it all, and it is 2:04, so I'm going to go ahead and, again, just remind everyone that if there were any unanswered questions that we did miss for one reason or another, the group from Light Brigade will address those with you one-on-one. And I would like to thank Light Brigade as well as John for the presentation and for everyone's time today. Thanks so much. Have a great day. We're going to sign off. Take care. Bye-bye.
Thank you.